Hi everyone, my name is Jad Silbak and I'm going to talk about explicit codes for poly-size circuits and functions that are hard to sample on low entropy distributions. This is a joint work with Ronen Shelter. Okay, so the focus of this talk is going to be about binary codes, and the setup we're going to have in mind is that we have some message M that we wish to send through some noisy channel. And to do so, of course, we first encode this message using some encoding function, adding redundancy to the message. So hopefully now, when we send this message through this noisy channel, the other party can apply a decoding function on this damaged code word and hopefully recover the original message. Now, given encoding and decoding functions, we say that they recover from a class or channel C if for every message M, the decoding of this damaged code word is the original message. And the ratio or the rate of the code is defined by the length of the message over the length of the encoding. And we want this to be as large as possible because this would mean that we didn't add a lot of redundancy. Now, this was for a single channel, but of course, given a class of channels, it makes sense to ask the following question. The first is, what's the capacity of the channel? And by capacity, I mean what's the best rate possible for this class of channels? And of course, it also makes sense to ask whether we can do this efficiently. Can we have an efficient encoding and decoding algorithms that are or achieve this capacity? Good. So what kind of families of channels do we usually consider? Well, undoubtedly, the most studied class of channels out there is, of course, Hamming channels. Now, HAMP is going to denote the class of channels that can change any Pn positions in the encoding. And this is an adversary in the sense that it looks at what we're sending, right? The channel looks at what we're sending, and it can tailor make or can decide where to put the errors depending on the message or the encoding of the message we're sending. Now, this type of adversary, of course, implies a notion of distance between every two code words. Even though this is the most studied class of channel out there, the optimal capacity of this channel is unknown. So for starters, we know that the capacity or the rate is strictly less than 1 minus entropy of P, and here h of P denotes the Shannon entropy function. On the other hand, we know that existentially, there are codes that achieve a rate that equals or are as large as 1 minus entropy of 2p. And of course, this is the famous Gilbert-Vacham. So the actual rate lies somewhere in between 1 minus entropy of p and 1 minus entropy of 2p, but we don't really know what the correct answer is. And this is a major open question that has been open for a lot of years. On the other hand, we have an also well-studied class of channels, and by this I mean the Shannon channels, or binosymmetric channels. And this is a channel that flips every bit with probability p. So if you had 0 with probability p, you're going to get 1, and if you have 1 with probability p, you're going to get 0, and with probability 1 minus p, you're not going to change the message. Okay? So this is not an adversary, in a sense that the actual error pattern does not depend on the message. Okay? However, for such channels, we do have explicit codes that achieve the optimal rates that equals 1 minus entropy of p. So it's possible to have explicit constructions for such codes, and this is very desirable. So we now have two extremes. On the one hand, we have Hamming channels, which are all-powerful in the sense that the only limitation on the channel is the amount of error it can induce. On the other hand, we have Shannon channels, which are weak in a sense that they don't even look at the encoding we're sending. They are independent of the actual code word or the message we're sending. Okay? And it makes sense to ask whether we can have a channel that is stronger than Shannon, but not all-powerful. So we want some adversary in a sense that it actually looks at what we're sending. Well, Lipton already considered such families or computation-bounded channels. For starters, these are a subset of HAMP. And by this I mean that they induce at most P errors. So there is a bound on the amount of error they can induce. But more than that, these channels are drawn from some computation-bounded class. For example, poly-size circuits, branching programs, AC0, and etc. So think of these channels as being limited in two resources. The first is the amount of error, and the other is the computational power. And the rationale behind this approach, of course, is that in real life, the actual error that is being induced to these code words that we're sending is, of course, not unbounded. The actual error patterns that are generated in real life are all computationally bounded in some sense. So it makes sense to consider this limitation or this relaxation. Okay, and in this talk, we're going to talk about poly-size channels. Specifically, we want codes that are good for poly-size circuits that induce at most P errors. And specifically, what I mean by this is that for any constant C, we want a code that is able to handle errors generated by size NC circuits that induce at most spin errors. Okay. Now, if you think about it, essentially all non-adversarial channels studied in information theory, such as burst channels, binary symmetric channels, and etc., can all be implemented in size NC channels, even for C that equals 1. So if you have a code for these kinds of adversary, then this gives a unified construction for all of these well-studied non-adversarial channels in information theory. However, there's still one problem, and that is, suppose we have a code that is good for size n channels, and recall that size n channels are non-uniform channels, then such codes are also good against Hamming channels. So this relaxation did not give us anything. And the reason is, well, suppose it's not, well, there are two code words that are of distance less than 2p from each other. And by using our non-uniform advice, we can hardwire this error pattern to be the distance between these code words, so that by applying this error pattern using this non-uniform advice, we can actually induce a decoding error. So what this means is that without any more relaxations, the relaxation on the complexity of the channel does not give us much. And the solution to this is stochastic codes, in which the encoding is going to be randomized, and the decoding is only succeeding with high probability. Now, let me retell the story of error correcting code, but this time for stochastic codes. And the story goes as follows, right? We have a message, we encode it, but this time we're going to give randomness to the encoding function. So the encoding function takes W, which is a uniformly chosen string. We send it through this noisy code word. This time we're going to specify it to be size n circuits, and they can induce as most spin errors. And the decoding function takes these damaged code words and hopefully produces the original message. Now, note crucially here that neither the channel nor the decoder receive this extra randomness. So this randomness is not given to the channel nor to the decoding function. So there is no setup in this scenario. We're not assuming anything. This is essentially what you would want in a non-setup case. Okay. So here's the formal definition. The definition says that given an encoding and decoding function, there are a stochastic code for class C. If for every message M and every C in this class of adversaries C, the probability of decoding actually recovering the damaged code word and outputting M is high over the randomness of W. Okay. Now for this talk, the error pattern or error is going to be n to the minus C, and you can choose any inverse polynomial you want. Okay. So what do we know about codes for polysize circuits? Well, let's start with the famous result of Goswami and Smith that showed that for every p between 0 and half and every c larger than 1, there exists a Monte Carlo least decodable stochastic codes for size n channels that achieve a rate that equals 1 minus entropy of p. Okay. Now, let's parse what's written here. First of all, let's start with the list decoding part. So by list decoding stochastic codes, I mean that with high probability, the decoding algorithm is going to output a list of candidates such that the original candidate is inside the list. Okay. So essentially the same as you would expect from list decoding, but only for high probability. And the Monte Carlo part says the following. It says that there exists a pre-processing stage in which the encoding and decoding are going to run in polynomial time, okay? And this encoding and decoding function have access to a random string that is chosen once, okay? This string is chosen once and uploaded to the cloud, and everyone has access to it, okay? Now, crucially though, this randomness could be larger than the size of the channel itself. So even though the channel can access this randomness, it does not mean that the channel is able to store it in its data or in its belly. Okay. Good. So even with this relaxation, it's really non-trivial to get explicit constructions that achieve these parameters, and this was the famous results of Goswami and Smith. And for people in the audience that are cryptographic, think of this as being a CRS or a URS construction. Okay. Okay. So let's recap what we know about the capacity or possible capacity for size n circuits. Well, for starters, we know that the list decoding capacity, both for Ham-P and for size n circuits, is going to be equal to the binary symmetric channel capacity equaling 1 minus entropy of P. So we plot this here in this graph, as you can see. On the other hand, we know that existentially, right, there are codes that achieve the rate that equals 1 minus entropy of 2p. Okay? and this is going to be plotted in this black line. So now the question is, well, what's the capacity for unique decoding? Well, Goswami and Smith already gave a partial answer for this. They showed that when p is larger than 1/4, then unique decoding is impossible, even for size n circuits. So let me plot it here. So it's consistent with the behavior we know for Hamming channels. That is, it is impossible to achieve unique decoding when p is larger than 1/4. And now a natural question is, well, what about the rest of the parameters of p? Can we say something non-trivial or something interesting when p is less than 1/4? Right, so this is the question of Goswami and Smith. Can we construct uniquely decodable codes for size n circuits that actually bypass the Gilbert-Vashamov amp? Okay, and by this I mean the dark line here. And the answer was yes. This is a result from last year, and we showed that it is possible to bypass the Gilbert-Vashamov amp. And in fact, we are able to achieve unique decoding for between 0 and 1/4 that equals the same parameters for the list decoding. That is, they equal 1 minus entropy of p. So we get the same rate as if we are in a list decoding setup for every p between 0 and 1/4. Okay? Now, let me emphasize that this is strictly better than what's possible for Hamming channels. So if you have a code that is good for size n circuits and it's optimal, as is stated here, then this code is going to be always better than what's possible for Hamming channels. And this is an explicit construction, which is nice. Let me also point out that the capacity function we get is not continuous. In particular, when p is equal to 1/4, the rate suddenly jumps from being strictly larger than 0 to being 0. Now, a natural open question that remains open, of course, is whether we really need this Monte Carlo part. And this Monte Carlo part is really not desirable because we're assuming a setup in some sense. And more than that, this is a bit cheating because the actual adversary can't really contain all the randomness that is public by this Monte Carlo construction. And note also that without a Monte Carlo assumption, the above codes imply circuit lower bounds. So we can't hope to do this unconditionally. But still, a natural open question, and we think an important one, is whether we can do this under hardness assumptions. And the main result of this paper is that it is possible to do this under hardness assumptions. And specifically, the hardness assumption we're going to use is a classic de-randomization assumption, which says that the class E is hard for exponential size non-deterministic circuits. Now, for people that are familiar with de-randomization, this is a variant of the well-studied and loved assumption that proved by that Pigalazzo and Wigderson used to prove that BP is equal to P. Okay, so Pigalazzo and Wigderson used a slightly weaker variant in which we're not assuming hardness against non-deterministic circuits, but only against deterministic circuits. But by this point, this is a standard assumption, even the non-deterministic version of it. Okay. So the strategy for how we get unique decoding is that we start with list decoding and then trim the list to get unique decoding. Now, though this is, of course, a natural approach and a straightforward one, let me point out, of course, that this can never work for Hamming channels. So something here happens that is not possible in the standard setup. So the main idea of how we do this under hardness assumptions is that we're going to use some hard functions to mark the correct message inside the list. Now, this is an oversimplification. Actually, it's kind of not correct in some sense, but it gives a correct intuition at least. So what kind of hardness assumption do we actually need? Well, usually when we talk about hardness assumptions in complexity, we talk on hardness on the average. So a hard function from n bits to n prime bits is hard to compute on the uniform distribution if for every c in this size n circuit and every x that is sampled from the uniform distribution, the probability that c of x is equal to f of x is small. However, for our application, this kind of hardness is not sufficient because the adversary can modify what we're sending. And what we really wanted or really would have liked, is to say that an adversary can't really generate any pairs of x and f of x. However, unfortunately and obviously, this kind of limitation can never apply, because if you think about it, a size n circuit can always be hardwired with roughly nc pairs of the form xi, f of xi. So just by the non-uniform advice, you can always be hardwired with such pairs. So we want a hardness definition that actually limits the ability of the adversary to generate such pairs. So I can't force or can't make the adversary unable to produce such pairs, but I can limit the amount of pairs it can produce. And this is the definition we come up with and we propose, and we think it's going to be of independent interest. And the definition says the following. A function n from n bits to n prime bits is HHJS for size n C circuits if for every adversary E of size nc that samples pairs of x and y, so the adversary takes randomness and samples a random variable of x and y, there exists a set H, and this set is only dependent on the adversary A, and this set is of size H, okay, such that the probability that x is not in H and that y is equal to f of x is small. So what this is essentially saying is that while I cannot stop an adversary from being hardwired with pairs of x and f of x, I can try to make this, to define a set in which it's hard to generate elements outside of the set. So in some sense, this is accounting for the non-uniform advice of the adversary. And note that when H is poly NC, this is essentially optimal. Okay, and this means that every pair that was generated was essentially hardwired beforehand. Good. Now, if you think also about it, this is kind of similar in flavor to multi-collision resistance hash functions. And let me also point out that unlike multi-collision resistance hash function, this is not a cryptographic setup. Our assumptions and techniques are going to be complexity-based or de-randomization-based, and this means that while the result of for multi-collision hash functions are able to produce or assume that if the function runs in less time than the adversary, in our setup, as is in the randomization in general, the runtime of the function f is going to be larger than the actual adversary. Okay. So now this definition also implies hardness for sampling. And by hardness of sampling, I mean that it's hard to sample a min entropy distribution, right? So A, when it samples the pair x and y, if x has sufficient min entropy proportional to the size of the set H, then it follows from our definition that it's hard to sample y, or it's hard to sample x and y such that y is equal to f of x. Okay? So one way to think about it, to see this, is, for example, think of a way in which you have this set. If you sample a random element from the set, then you get a min entropy distribution proportional to the size of the set. Okay? Now, this is similar in spirit and in ideas to the result of Viola on hardness of sampling. And let me just point out subtle differences. The main focus of these results was on sampling or hardness of sampling for the uniform distribution. However, a careful examination of these results revealed that he actually also considered a variant of the definition we propose. And also one focus of this work is that he focuses more on weaker variants of, or weaker classes of channels that you can also hope to get unconditional results for. Okay? Good. So let me now plot out the hierarchy of these of hardness as we state them in this paper. So the first or the strongest we want to point out here is the notion of hard to sample function we proposed a moment ago. Okay? And as we stated a moment ago, this implies that it's hard to sample on low entropy distributions or sufficiently high min entropy distributions. And this also implies that it's hard to compute on sufficiently high min entropy distributions. So if it's true that for every x sampled from size n circuits, nc of size nc, the probability that c of x equals f of x is going to be small whenever x has sufficient min entropy. Okay? And of course, this implies hardness on computing uniform distribution. So this gives us a hierarchy, at least, of the hardness assumptions or hardness of these kinds of results. Let me point out also that it's really harder to get hardness for sampling than it is to get hardness for computation. Okay, so hardness of sampling is difficult or more difficult to achieve than hardness of computation. And one key example you can have in mind is that suppose we have a one-way permutation P, and this one permutation, using this one-way permutation, let's define f of x to be the inverse of P on x. And obviously, right, given it's hard to compute f of x given a random x, because this would imply breaking the one-way permutation. So this function is hard on the average. However, it's really easy to sample pairs of x and y together. Okay? And the reason is, well, first sample y at random, and then apply p of y, or p on y to get x. And of course, this would be of the correct distribution because x is going to be uniform. Okay? Now, what this shows is that even though we had a function that is hard to compute in the average, this does not imply that we had that we get a function that is hard to sample on the average. Okay. So, with this in mind, let me state our formal result. So here's our definition, the definition for hard to sample functions. And the first result is that we're able to get, assuming E is hard for exponential size non-deterministic circuits, the same assumptions we get in our result, is that there exists a function f from n bits to n, let's say n to the power 3 or n to the power 4, that is HHTS for size n circuits, and H that is poly in NC. And to the best of our knowledge, this is the first construction for such functions for sufficiently low min-entropy distributions. So we're not aware of any hard-to-sample functions that are hard to sample for such small min-entropy. One more thing to point out here is H is essentially optimal, right? You can't hope to get better size H than this. And one caveat of this is that unfortunately the size is going to be, f is going to be enlarging. So f is going to take n bits and it's going to output more than n bits, okay? And for some application, we want f to be shrinking. So our second result, which is technically a bit more complicated to achieve, is that under the same assumptions, we can get any kind of linear shrinking we want. However, the set size is going to be larger, and it's going to be h to the 2 to the delta n. So it's medium size, I would call it medium size, and f is going to be shrinking. Okay, so it's the same assumption. And this time you can choose the shrinking of the function f. However, you don't achieve optimal h. So in a perfect world, we would get an optimal size h and a shrinking function. And in fact, we could hope to get a shrinking that is almost logarithmic. Okay, so let's recap. In this talk, we saw an explicit binary uniquely decodable codes for size n circuits, and these codes achieve better result or better parameters than what's possible for Hamming. Okay, and we propose a new notion for hard-to-sample functions that we think is going to be of independent interest. And open questions is going to be that, well, can we improve this assumption on the hardness of E? And can we just assume hardness against deterministic circuits and not non-deterministic circuit? The other thing is, well, can we find more application for hard-to-sample functions? We think there are interesting applications for hard-to-sample functions yet to be discovered. We already have a result in Eurocrypt that used hard-to-sample functions to get better non-malleable codes for poly-size circuits. We think these application can be, or more application can be found in cryptography and in complexity in general.